Subchapter 6.2 Otto cycle. The ideal cycle for spark
goes to the process 41 where the process is an
isoconstant spark ignition engine that obeys Otto cycle. Besides piston, intake valve, exhaust valve, and cylinder, the spark ignition engines having a spark plug that will be used in their operations. In the actual 4-stroke spark ignition engine, there are 4 strokes involved. Intake stroke, where the piston will move from top dead center TDC to bottom dead center BDC, drawing a fresh charge vaporized air and fuel mixture. During this stroke, the intake valve will open and the exhaust valve will close. Next is compression stroke. During this stroke, the piston will travel from bottom dead center to the top dead center. As the piston rises, both intake and exhaust valves are shut. In this stroke, momentum from the flywheel will drive the piston upward and compressing the fuel and air mixture. Power stroke or expansion stroke. As the piston reaching the top dead center, the spark plug will fire and igniting the compressed fuel air mixture. The air fuel mixture will burn in a nearly constant volume manner. The gas will then expand and pushing the piston downwards. At this stroke, both intake and exhaust valves are closed. And lastly, the exhaust stroke. At the end of power stroke, the exhaust valve is opened by the cam mechanism on top. As the exhaust valves open, the high pressure and temperature of the gases will drop rapidly, although the position of the piston is still at the bottom dead center. And this occurs in nearly constant volume manner. The piston will then move upward and exhausting the burnt gas or product out from the cylinder. Since during the intake stroke and most of exhaust stroke operated approximately or equal to the atmospheric pressure, analyzing these processes will not affecting much on the result. Therefore, in most cases, these processes can be neglected. The ideal Otto cycle can now be designed as shown in these diagrams. With respect to the diagram, process 1 to 2 is the isentropic compression where both pressure and temperature increases. For the power stroke, the combustion process is considered as constant volume heat addition from external source, such in the process 2 to 3 that further increase the pressure and temperature to the maximum value. During the expansion of gases that pushes the piston downwards, it is modeled as isentropic expansion as shown by process 3 to 4 where the pressure and temperature will drop. And once the exhaust valve is open, it will be assumed as the constant volume heat rejection. During this process, the temperature and pressure will return back to its original state. The process will be repeated as cycle. Note that this cycle only involves with heat transfer coming in and going out from our system. There are no work involved for the Otto cycle and other cycle for internal combustion engine. Here are the summary of the processes involved and the related formula that can be used in our analysis later. For the process 1 to 2, where we have isentropic compression, and for the process 3 to 4, for the isentropic expansion, we can use the isentropic relation to find the required properties. Meanwhile, for process 2 to 3 and 4 to 1, where we have constant volume heat addition and constant volume heat rejection respectively, we are going to use the non-flow energy equation to find the heat transfer. From the non-flow energy equation, NFEE, for isochoric process, we know that the change of heat transfer is given by Q net in is equal to Q in minus Q out is equal to the change of the internal energy. Therefore, Q in minus Q out is equal to U out minus U in. And for gases, the internal energy U can be determined by the formula of U is equal to CV times T. Therefore, for the heat transfer in the unit of kilojoule per kilogram, we can have this expression. Thus, we can have this equation with respect to the specific processes. We also can find the required properties based on the processes. For example, process 223 is isochoric process and it is obey the law of P in over T in is equal to P out over T out, or in our case, we can use P2 over T2 is equal to P3 over T3 to find the required properties. Same goes to process 41, isochoric process. We can use the relation of P4 over T4 is equal to P1 over T1 to find the required properties. For the thermal efficiency, the essence will be the same as the thermal efficiency that have been discussed in previous chapters, and it is given by thermal efficiency is equal to work net out divided with heat transfer in. For the case of a cycle, work net out is equal to Q in minus Q out. For Otto cycle, we can also obtain the relation for the thermal efficiency such as this expression. Now let's have a look at the derivation for this relation. For this equation, we can say that the thermal efficiency depends only on the compression ratio, RV. Although in the ideal Otto cycle, we assume the heat addition and heat rejection process is done externally, however, they are not efficient for the operation. For greater practicality, the heat addition process is done internally, while the burnt gas is exhausted externally. And that is why it is called internal combustion engine, ICE.